start with. So last week we were looking at properties of the derivative. So we're going to continue doing that now. What we did last week was we proved the initial basic properties. We proved that the process of differentiation was a linear process. Theorem 4.5. We proved the product rule, theorem 4.6, which is a nice rule that related derivative of a product of two functions, related that to the individual derivatives of two functions. And we were able to prove that by using our limits definition of the derivative, and together with the general properties that we've already accumulated about limiting processes. So today we're going to focus on some of the other properties, chiefly the chain rule and the quotient rule. And we're going to prove them in a slightly different, slightly different order to how they're done in the book. So we're going to start thinking about the quotient rule first. So this is towards a proof of the quotient rule. Quotient rule, remember, is applying to this situation where you've got functions u and v. You've got functions u and v. U and v, say, are functions in the real numbers to the real numbers, or some subset of the real numbers to real numbers. These are two real value functions, and we form a new function y, which is the quotient of those two. And we want to know how the derivative of y relates to the derivatives of u and v. Okay, now we have the statement of the quotient rule telling us what that relationship is. It's v du, v times the derivative of u minus u times the derivative of v divided by v squared. You may know that well already, having used it before, but we'd actually like to see a proof of it, justification. But also in a way where we want to make use, we want to try and avoid having to replay arguments that we've already played. So we've already proved the linearity and the product rule of the derivative. So we want to make use of those as much as we can. So we've already proved the product rule. The quotient rule, it doesn't look a million miles away from the product rule. Still got that structure where it's one function times the derivative of the other, plus or minus the other function times the derivative of the other one. So it's kind of reminiscent of the product rule in some sense. So we've already proved the product rule. So with that in mind, we can rewrite, just doing this, looking at y in a slightly different way, rather than thinking of it as y equals u divided by v, let's think of it slightly different. I mean, it's the same thing, but let's think of it like this. It's u multiplied by 1 over v. So that shows the presence of a product of two functions. So we could use the product rule to get a derivative of y in that case. So maybe we could apply, we've already proved the product rule, so maybe we could apply the product rule. However, before we do that, we would need to know how to differentiate this second factor, this 1 over v. We can take it, we can assume we know how to differentiate v, because we just want to find the derivative of y in terms of the derivatives of u and v. But even if we could put down the derivative of v, how do we deal with the derivative of 1 over v? Well, we can rewrite this again let's write it like this. Y is equal to U times the composition R after B. Another way of viewing Y, again using the product operation between functions and the composition between functions. But what's this R? This R, where R is the reciprocal function. Defined by R of X equals 1 over X. And that circle is composition of functions. Now, we've already stated the chain rule. The chain rule allows us to deal with compositions of functions. So if we can use the chain rule, now we haven't proved the chain rule yet, but we'll prove that in a moment. If we can use the chain rule and know how to differentiate R, then we could prove the chain rule, prove the quotient. I'm going to carefully motivate things here. Explain why I'm doing it this way. So rather than tackle the quotient rule head on directly, because I can see really it's the presence of a product operation. I've already proved the product rule. And that 1 over b I can think of as a composition of functions. It's the reciprocal function applied after the function b. 1 over b of x is equal to the reciprocal of b of x. The chain rule, once I've proved it, allows me to say what the derivative of a composition of functions is. So this is the kind of roundabout route that I'm going to prove the quotient rule. We'll go ahead and we'll prove the quotient rule now using the chain rule. Then afterwards we'll prove the chain rule, and then the whole thing will hang together when it's proved. So first I want to consider R. Consider this function, the reciprocal function, R of x equals 1 over x. Can I say what the derivative of this is going to be? Well, we'll just go straight back to the definition of the derivative. This isn't too hard to work out. The definition of the derivative says this is the limit as x approaches a of R of x minus R of a all over x minus a. It's just the definition of the derivative. It's true by definition. Can I figure this out in a sensible way? Well, yeah, because I know what the function R is. R is the reciprocal function, so this is 1 over x minus 1 over a, all over x minus a. Now, you can't just evaluate this limit by substituting x equals a into this expression here, because if you'll first of all, you'll have a 0 on the bottom, and you'll have a 0 on the top as well. So you can't make sense of that limit directly. But really there isn't really a 0 in the denominator, because if you examine this fraction closely, you'll see that this factor actually cancels out of the top and bottom. And the way to see that is to simply add together those two fractions on the top. So how do you add together 1 over x and 1 over a? Well, you need to put it over a common denominator, which is going to be x times a. Still got x minus a on the bottom. You put that over the common denominator, x times a, and you'll have a minus x. This is just subtracting these two fractions. So the common denominator x times a, and it's then a over xa minus x. So that's just the rule for adding fractions. But then what you see is, maybe just flip it around and change the sign. I can change the sign and make this minus x minus a over xa all over x minus a. Okay, introducing this minus sign here just changes the order. I've just done that to make it look nice, really. And so we can plainly see now that there is a common factor of x minus a in the numerator of the big fraction. It happens to be in the numerator of this subfraction, but there's a factor of x minus a there, which we can easily cancel out, and there's a factor of x minus a in the denominator. And I can cancel out that. That doesn't encounter any problems of dividing by 0 or anything, because we're taking the limit as x approaches a. So x is never actually equal to a in that limiting process. It's just getting closer and closer to a. So this allows us to rewrite this as the limit of minus 1 over x times a. Okay, that's what's left behind when I cancel out x minus a in the top and bottom of the fraction. So a 1 in the denominator and a 1 over xa in the numerator. And this limit we can now simply evaluate just by substituting the limiting value of x, a, and it's going to give us minus 1 over a squared. All of this would only be valid, of course, only if a is non-zero. The reciprocal function is not defined at 0 anyway, so you can't define the reciprocal function at 0. So everywhere away from 0, you can differentiate the reciprocal function, and it has that. That was what we expected. We're probably familiar with that already, is the derivative of 1 over x, i.e. the derivative d dx of 1 over x is indeed minus 1 over x squared, as expected. We're already familiar with differentiating 1 over x, x to the power minus 1, gives you minus 1 over x. Okay, that's good. We know how to differentiate the reciprocal function now. So now we'll return to so assuming the chain rule for the moment. Let us prove the quotient. So remember, we'd organized our quotient y as u over v. We'd organized that as u multiplied by the composition of r after v. See, now all the ingredients that are in this quotient u over v, when you look at it like this, I know how to handle all those ingredients. I can differentiate u and v. I'll just write down the derivative of u, the derivative of v. That's the kind of thing I'm looking for. I'm looking for some recipe for the derivative of y in terms of the derivatives of u and v. But the other ingredients, or the other glue that's used to glue u and v together here, okay, it's the quotient u divided by v, but this way of looking at it, it's the product of the composition of the reciprocal function and v. I know how to differentiate a product using the product rule. I know how to differentiate a composition using the chain rule. And I know how to differentiate this particular function, r, the reciprocal function. It's got the derivative minus 1 over the square of its argument. Okay? So, the derivative of y at a. So first of all, we apply the product rule. It's going to be u of a multiplied by the derivative of the other function at a plus the other function r composed with v applied to a, and the product of that with the derivative of u. The derivative of u. The derivative of u evaluated at a. So that there, that line is just the product rule. Differentiating a product. this function u times this function in the brackets. It's this function u multiplied by the derivative of the function in the brackets plus the function in the brackets multiplied by the derivative of u. And that's straight away the product rule. Then this one here, I need the derivative of this quotient of this composition. So that I can use the chain rule, and the chain rule is going to be the derivative of r evaluated at v of a multiplied by the derivative of v applied to a. So that's the application of the chain rule to this composition here. The derivative of the outer function evaluated at the normal argument v of a multiplied by the derivative of the inner function v. There, and then I've still got this here, r after v plus a, so that's by the chain rule. Again, it just looks like a complicated mess at the moment. It doesn't really look like the result of the quotient rule that we're familiar with. But when you bring in the see, we're free now to bring in the definition of the function r and the definition of its derivative. So this is u of a. Now what is r? What is the derivative of r evaluated at v of a? Well, the derivative of r evaluated at v of a is 1 minus 1 over the square of the original argument. It's minus 1 over v squared a, and that in turn is multiplied by the derivative of v at a. That's good. Then what is r composed with v at a? That's simply 1 over v of a. Okay, the reciprocal after applying v to a. So you apply v to a, then take the reciprocal. Definition of it. And that's multiplied by u prime. So that's by definition of r and r prime. Now this is starting to look more like the quotient rule. You've got products of u with the derivative of v and something times the derivative of u, and you've got a 1 over v squared there. Maybe a 1 over v here, not quite right yet. But now we're basically going to add these two terms together, and there is a common denominator there of v squared a. See it there? So on the left-hand side, you've got minus u prime, u evaluated at a times v prime at a. And on the right-hand side, well, we've got u prime of a, the derivative of u at a, but that's only divided by v of a. So to put it over this denominator, v squared, we've got to multiply it by another v. It's v of a times the derivative of u at a. And that, when you look at it, that's exactly the quotient. Okay. Y is u over v. What's the derivative of y? The derivative of y is, well, it's all over v squared, and it's v times the derivative of u minus u times the derivative. It's exactly the quotient. Remember, this is y prime a on the left. So this is exactly the terms in the numerator are given in the other order. But apart from that, this is exactly the claimed quotient. So that's good. Any queries about that? I really like doing it that way because it ties together. It's on the way we dealt with the reciprocal function. We looked at the reciprocal function, we proved what its derivative was, and then we also see how, results we've already proved, like the product rule and the property of the reciprocal function, combined with another property, the chain rule, which we haven't proved yet, but we will now shortly. And you can put those properties together, and it means you can prove the quotient rule without having to do a limiting argument. We avoided here in this little argument here on this page, if you're looking at it now, we avoided that explicit limiting argument. We just were making use of the previous results about differentiation that we'd already proved. Okay. And maybe chain as well. So again, it shows you the way, that establishing these mathematical theories involves, building results on previous results. Putting previous results together in new ways in order to get new results. Okay. So this just leaves us needing proof of the chain rule. To complete our main properties, properties of the derivative. And I was thinking of just forging ahead, but I think maybe I'll measure my progress a little bit more and say, well, maybe just indicate why maybe for the chain rule we need something different. So I'm not going to forge ahead and get the full treatment of the chain rule, but let's just try and do a quick, simple proof of the chain. Okay, the product rule was easy, linearity was easy, well, not easy, but it went through easily enough by just interpreting the definition of the derivative in the right way and using what we already know about limiting values to get the proof out. Okay. So consider a composition. So suppose f equals g after f. Suppose g and h are differentiable. Okay, so the usual question, how does the derivative of f relate to the derivatives of the ingredients of f? Question. Okay, the chain rule tells us what it is. The chain rule says the derivative of f at a is the derivative of g at h of a multiplied by the derivative of h at a. So let's try a proof of this. That's the chain rule. So let's try to prove it. And the derivative of f at a, by definition, is the limit as x approaches a of f of x minus f of a over x minus a. And this is our usual limiting value of the relative change in value of f relative to the change in value in the argument. This is the geometric meaning of these taking the limit of the gradients of these chord lines across the graph of f from a point x to a point a, and then taking the limiting value of the gradients of those chord lines. And the function is nice and differentiable. They converge to this limiting tangent line, which embodies the instantaneous rate of change of the function f at that point a, and so that limiting value of the gradient is called the derivative. So there's the definition of the derivative involving f. We know what f is defined as. F is the composition of g and h. So what we're looking at is the limit as x approaches a of g h of x minus g of h of a, and that's all divided by x minus a. Okay, so there we're using the definition of f as the composition of g after h. And this is where we maybe stumble a bit, maybe pause a bit. It's not so clear how to proceed from here in the same way, the same easy way that we did when we were proving the linearity result. We put down the definition and we were able to just continue through, keep manipulating this limiting value using what we know about limiting values, and we got the linearity result. Same thing with the product rule. We wrote down the definition, we examined the quotient, the fraction, we manipulated the numerator in a clever enough way, but still just using algebra, manipulated the numerator and applied what we knew about limiting values, linearity, and so on, and that got us the product rule. But here it's maybe just a little bit, it's kind of harder to separate out the G and the H here. Because this H is, you know, in order to get the quotient rule, you're somehow going to have to separate out G from H, and you know, H is inside this argument to G here, and it's also inside this argument to G here. I don't know anything specific about the function G, H for that matter. They're just general functions. I'm trying to keep things generic here, so it's not so clear. It's not so clear how to proceed. In as easy a way, easy quotes, hard to understand, but as easy or straightforward a way as before, when we were proving linearity and the product. Okay, so what I'm trying to motivate and suggest by that is maybe we need a different way of thinking about it. Maybe we need something a little bit more. There are ways to push it forward here to fiddle around with this, but I don't think they're as easy to spot, and there's some slight technical difficulties with them. So next time we will prove this. Next time we'll approach this property, meaning the chain rule. We'll give a proof of it, but using a reformulated definition of the derivative, an alternative viewpoint or an alternative way of thinking of the definition of the derivative. So that'll be nice. I mean, it's still the same derivative. It's still more or less the same thing, but it's just a slightly different viewpoint on the derivative, which is very useful to have as well. So we'll see that next time. So it's good to see things not working out so easily sometimes as well. I don't want to get the impression that everything's easy in mathematics. Sometimes things are tough. Okay, so for the remaining few minutes, I wanted to look at a few further things we can do with the derivative in the notes. So this is beginning kind of halfway down page 46. And these are like kind of further properties or further techniques for differentiation that we can use. I'll move fairly quickly through them. Some of them you might be familiar with already, some maybe not. There's some worked examples here. And then there's more exercises at the end of the chapter, and those are the ones I'd like to set as tutorial questions for this week. So the first idea is looking at inverse functions. So you're familiar with the idea of a function. Sometimes if the function is not, well, if the function is bijective, if it's one-to-one and onto its codomain, then there will exist an inverse function. And So the question might be is, well, how does the derivative, if a function is differentiable and it has an inverse, how is the derivative of the inverse function? Is there any nice relationship with the derivative of the inverse function to the derivative of the original function? We'd hope that there would be, okay? Because a function is kind of intimately connected with its inverse. The inverse function is kind of the same operation as the original function, but done in the opposite direction. So it's a very, the two are really just mirror images of each other. So surely there should be a strong connection, hesitate to say, but almost a mirror image connection, probably between the derivative of a function and the derivative of its inverse. And it turns out there is. And you can kind of argue for this with a nice geometric explanation. So here in red, it might be some original function f. And we'll presume it has an inverse. Kind of looks like it does have an inverse over this range of values anyway. And its inverse will be this function g. And there's a very clear geometric relationship between the graph of a function and the graph of its inverse. So as I said, the inverse function g to f, well, g is basically does the same operation as the function f, but backwards in the opposite direction. So the graph, when we're looking at the graph here, we've got the x-axis and the y-axis, and the graph is tracing through all the points x, y in the plane that are related by y equals f of x. Okay, but this point here is over this point x here, and the y-coordinate is the value of the function, y equals f of x. But the inverse function is just the same relationship in the opposite direction. So all you're doing is interchanging the roles of the x and y coordinate. Geometrically, how you do that is you look at your xy plane, you just pick it up and you flip it, you reflect it in this main diagonal. And that interchanges the x and y axis. If I reflect the whole plane in this main diagonal there, that 45-degree line, it interchanges the x and y axis. The y axis becomes the x axis becomes the y axis. So the graph of the inverse function of f will just be the reflection of the graph of f in that line as well. The mirror image of f in this line. So it'll be this line over here. Well, when you understand that, it's very easy to see what the relationship between the derivatives is. The derivative at this point P is the slope of this tangent line. The slope of this tangent line, you can visualize a right angle triangle here, and the slope of the triangle is the vertical distance divided by the horizontal distance on the triangle. That's the gradient of the hypotenuse from here. So what happens to this triangle under the reflection thing? Well, it reflects to this triangle here. The vertical side becomes the horizontal side. The horizontal side becomes the vertical side of the reflected triangle. So what's the gradient of this? And the tangent line becomes a tangent line to the graph of the inverse function. The gradient of the tangent line, again, will be the ratio of the sides, the ratio of the length of the sides of that triangle. But that ratio is going to be the reciprocal of this ratio. Because this one, it's this long side here divided by this short side, vertical divided by horizontal. This gradient is the vertical, which was the short side here, divided by the horizontal, which was the long side. So you're flipping the gradient, applying the reciprocal operation to the gradient. So in other words, what that means is the relationship between the derivatives, dx dy, and dy dx, where the relationship between x and y is given by the function f in one direction and the function g in the other direction. The relationship between these two derivatives is the reciprocal relationship. Okay. So the derivative dx dy is 1 over dy dx. Okay. So at places where these points P, they both kind of nearly have gradient approximately 1. But at locations where the function f is a very low gradient, where the function f is nearly horizontal, not increasing or decreasing very much, what will its inverse function look like? The inverse function, so if the red graph is very not steep, almost flat, the reflected function will be nearly vertical, will be very steep. So a low gradient for f will produce a very high gradient for g, because you're doing this reciprocal. You have a very low number for dy dx, the gradient of f. You do 1 over it, you're going to get a very high number. So that's a nice relationship to have. The other idea is parametric differentiation. So sometimes we, remember, we define the idea of the derivative in terms of tangent lines to curves, or at least we defined it that way geometrically. The derivative is the gradient of the tangent line to a curve. So these are perfectly good curves here that we're looking at, these red curves. However, there isn't a single function that can, there isn't a single function y equals f of x which has these curves as its graph, okay? Because there can't be, because these curves, they can't be given by functions of x, because for instance, say here, this value of x of 4, if x is equal to 4, what is the value of f of x? Well, you kind of want it to be up here, 2 and a bit, and you also want it to be down here, minus 4 and a bit. Okay, but functions can't be double valued like that. Functions have to be single valued. So a function y equals f of x, if x is the horizontal axis and y is the vertical, it could never have a graph like this. Similarly, I mean, you can get this curve as a function x equals f of y. So if you look at it with the y-axis as the horizontal axis, kind of sideways like that, then it does look like the graph of a okay function y x equals f of y. But at least not from the orientation y equals f of x. However, this one, whatever way you look at this one, because the curve is a closed loop, it goes around like this, and there's a twist, and then it goes around again. It's a closed loop, so you'll never be able to embody that curve with a single function, x equals f of y, or even y equals f of x. Okay, just can't be done, because whatever, you know, if you want, what's the y coordinate corresponding to this x coordinate, well, you want it to have very low y value and a very high y value. So there's 2 points in the curve, over that value. But that's not to say you can't describe these curves using functions in a different way. You can, and this is what we know as parametric curves. So this is where you describe the curve by giving 2 separate functions, one for the x coordinate and one for the y coordinate of the points. And both these functions depend on a new other variable t, and you generally think of t as like a time-like variable. So as you run the variable t through various, as you run t through all values of time, the point xy traces out the curve. Okay? So you could imagine for a certain t value, the x and y coordinates will get this point down here, and as t increases, as t increases, the point moves along the curve and traces out the curve. The particular functions for this one are t squared for x and 2t minus 1 for y. And this one down here, x and y are both given as combinations of cosines and sines. So, okay, so this is one way, another way that curves arise, different kinds of curves in the plane. But we'd still like to talk about the slopes of the gradients to these curves. We'd still like to be able to get at that information. And it surely must depend on the derivatives of the coordinate functions, the derivative of x with respect to t and the derivative of y with respect to t. We would hope there'd be some nice clear relationship there. Right? What the slope of the gradient, what the slope of the tangent line to any of these curves is. So indeed there is. So the way to think about it is so if we had a tangent line drawn here, we'd like to get the gradient, meaning the tangent of the angle that the line makes with the positive x-axis. So in effect, we'd like to get the derivative dy dx. And so the trick here is a little derivation using the chain rule. We think of y as a function of x, so that we can talk about the derivative dy dx, but then that would also mean that y is a function of t through x. So y is the composition of x after, y is the composition of this function y after x. Okay? So you can apply the chain rule. So we have y as a function y of x, but x is a function of t. So we can get the derivative dy dt. Using the chain rule, that's going to be dy dx multiplied by dx dt. It's an application of the chain rule there. And then reorganize that equation so we isolate the derivative dy dx. You just need to divide both sides by the derivative dx dt. So you get this expression that dy dx is dy dt multiplied by 1 over dx dt. So yeah, the two derivatives of the two coordinate functions, the x function and the y function, their derivatives with respect to t, they combine together in that way to give you this quantity dy dx. And so when you take that and evaluate that expression at a certain value of t, it's going to give you a dy dx value for that value of t. So that's going to be the gradient of the tangent line to the curve at that point t. Okay? Remember, points on these curves correspond to values of the parameter t. So that process is known as parametric differentiation. Parametric differentiation. And another important property is implicit differentiation. Again, this is another application of the chain. We may have relationships between x and y that are not necessarily specified from the get-go as a function y equals f of x or y equals y of x. That's the cleanest kind of functional relationship between two quantities x and y. And we can take the derivative of it by just hitting it with the definition of the derivative straight away. However, we may get relationships between the two variables x and y defined in a non-functional way through some other kind of condition or equation imposed on the two variables. For example, like these three here. It could be said that the sum of the squares, x squared plus y squared, is always 1. It could be said that x squared minus y squared is always 1. Or it could be said that the sine of x times y equals 1. Now, it may be possible to rewrite these relationships and convert them into normal functional relationships of giving you y as a function of x. However, it isn't always possible to do that, or it isn't always easy and clean to do. So we would like to have some way of obtaining values for the derivative dy dx, say, without first having to explicitly go and rewrite the thing as a clean, convert the equation to y equals some expression just involving x. Well, we can do that with the use of the chain rule. So here's an example here. We've got this polynomial equation, complicated order 2 polynomial equation in x and y. So this would define some curve in the plane, okay? Because there are only certain pairs of points x and y which satisfy that equation. You could plot them all in the plane and you would see some kind of curve. And so we'd like to be able to get at gradients of the tangent or values of the derivative, dy dx. So can we get at dy dx without first reorganizing that equation to y equals something volume? So yeah, we can. What we do is we just accept, we kind of presume that y in the background, there is some functional relationship, y equals y of x. And then we just proceed, and this is the key step, we differentiate both sides of the equation with respect to x. Okay? And when you differentiate both sides of the equation with respect to x, well, on the right-hand side, you've got a constant, dy dx of 4, so it's 0, constant. But on the left-hand side, you've got a combination of terms. Some terms are just functions of x, x squared and 2x. You just differentiate those in the normal way, 2x and 2. Other terms, though, are functions of y or y and x. But if you think in the background that y is a function of x, then we can apply the chain rule, because these are compositions. This is like a function of y squared, but y is in turn a function of x. So applying the chain rule to differentiating 2y squared, we would get 4y multiplied by the derivative of y with respect to x. So that there is an application of the chain rule. Similarly here, we'd have to apply the product rule and the the product rule to x times y. So it's going to be x times the derivative of y divided by dx minus y times the derivative of x. We're differentiating with respect to x, so the derivative of x with respect to x is just 1. That's why it's just minus y. So you apply chain rule, product rule, things like that as you go, and you get this quantity dy dx popping up in various locations. So then that equation, we make dy dx the subject of. So this equation is rewritten. We send every term not involving dy dx over to the other side and factor out the dy dx. As a factor of 4y minus x on it, so you divide both sides by that. So eventually you get this formula for the derivative of y with respect to x. Now it involves the variable x, and it also involves the variable y. Okay. But at least it gives you an expression for what the gradient of the tangent line to this curve will be based on the values of x and y, based on the coordinates of that point. Okay, I've just run out of time there. I'll leave you to read that last one, logarithmic differentiation, on your own. You can read it there, and there's a little example shown there. But then for the tutorials this week, that opens up. Remember, next week we're going to go back to the chain rule and deal with that and give you an alternative view on the definition of differentiation. But for the tutorials this week, any parts of these initial questions you haven't dealt with, so still if you need to deal with some parts of question 4, but then there's also a series of other questions, I think all the way up to question 8. So 5, 6, 7, 8, those questions will be open up for the tutorial this week as well. Okay? Okay, thanks for your attention. I better finish up now.